Hello and welcome back to the Economancer, where we explore the magic of public policy, cybernetics, economics, philosophy, and theology. Well, it's a lot going on, I know. So I'm your host, the High Priest of the Economicon, and today we're taking on a thrilling new quest, venturing into the intricate labyrinth of Peter Kennedy's A Guide to Econometrics 6th edition. So I want to make something clear about this video series. This is going to be more along the lines of like a high altitude picture of what's going on. There will be some breakdown of the math, but that's not going to be my focus. There's a lot of better mathematically focused applied econometricians on YouTube, and I don't want to take into their space because I think that they'll do a better job anyway. But I do want to give my point of view, especially as an applied econometrician focusing on public policy with respect to cybernetics, etc., and how this would work. Because one of the things that people don't understand is the importance of econometrics when it comes to public policy, when it comes to all of these different things that happen in our lives. So this is something that someone, who's a high level econometrician, they may not necessarily need. There's probably still going to be some interesting information as I apply some cybernetics behind it to it. But also for the layman who's like hearing about all this economic data and economic statistics are really trying to figure out what's going on and how to understand this best. So this is what we're going to be doing. We're going to be introducing this. We're going to be looking at the fundamentals of econometrics. So this is a crossroads where we have economic theory, statistics, and mathematics. They meet to unravel these intricate realities of economic behavior, whether this is a choice model, whether this is an understanding of gross domestic product or trade, etc. All of this gets brought out. So in our econometric exploration, something really important here is we're going to be talking about estimates and estimators. So estimators are rules that allow us to crunch observed data and produce estimates, which are calculated values of those population parameters. Estimators can be thought of as the recipe, and estimates are the meals that get served. Not all estimators are created equal. We prefer good estimators, which generate estimates that are closer to the true parameter values. Preferred estimators are not only good, but also fulfill certain criteria, which we're going to be delving into in this next piece of this video. Now, we have the disturbance term. That's the unobserved errors or the noise from information theory that can't be explained by our model. So accounting for this is crucial to obtain reliable results. Boom. Now, before we dive into the second part, if you're finding this video informative and engaging, don't forget to hit that like button and subscribe to the channel for more insights into the world of econometrics and cybernetics. So, in chapter 2, we explore the criteria for estimators, going beyond good and diving into the realm of preferred. One of the methods we encounter is the least squares. This is a workhorse model in econometrics, which all it's doing is minimizing the sum of the squared residuals to find the best fit line. It's simple, intuitive, and often yields efficient and unbiased estimates. And you can look at this and you can see that's approximately where you would probably draw the line on this, because it's very important to understand that least squares when it comes to this, it's the most simple and it's the easiest to think about because it's probably the way that our mind works most of the time when we're trying to make a straight line on some values. All right, so now we're going to be talking about R squared, which is always something you hear talked about when it comes to any type of econometric, psychometric, etc. That tells us the proportion of the variance in the dependent variable that can be predicted from the independent variables. Higher R squared values indicate a better fit for the model. Let's delve deeper into this higher R squared. So the R squared, known as the coefficient of determination, is the square of the correlation coefficient between the actual dependent variable, y, and its estimated counterpart, y hat. But we have to remember, R squared is sensitive to a range of variation of both the dependent and independent variables. A wider range of independent variables will inevitably cause a wider range of dependent variables, so affecting the R squared. If we have the same unexplained variation or sum of squared residuals, squidgels, in two different models, the relative importance of that unexplained variation can differ significantly depending on the variation in the dependent variable. And while many may be inclined to chase this higher R squared, let's clear up a misconception. A good estimator in econometrics is not necessarily one with the highest R squared. So while it's an interesting metric, it doesn't solely dictate the quality of an estimator. And what I mean by this is like, you can look at psychometric data. Like an R squared of like 0.2 is really high. So that's 20% of the variation is caught up in your model. That's really good considering that's what you would expect to be the differences between person to person. And so if you're taking up 20% of the variance between person to person, that's quite a bit considering how different and disparate each person is from another. So we also need to think of this mean square error. So this is a criterion that combines an estimator's bias and variance, and this provides a more comprehensive measure of its performance. Okay, so asymptotic properties. So asymptotics deals with how estimators behave as the sample size grows to infinity. A desirable property here is consistency, meaning that as we gather more data, our estimator converges to the true parameter value. We delve into the maximum likelihood method later on. So you can see here in this graph, I mean, it's pretty cool. Thank you. You're welcome. I'm glad I did it. As the more sample size, so sample size of 100, that's going to be the blue. The sample size of 1,000, that's going to be red. And the sample size of 10,000, that's going to be that green. And you see this f of x, this is like the true parameter of what's going on. That's the true mean. So as we gather more data, we're going to be getting closer and closer to what the true population value is. And there's a lot more to go into this that will keep building on. But again, this is just an introduction to what's going on here. All right. So we have other methods such as maximum likelihood method. Now, what is the maximum likelihood method? This is a powerful statistical technique estimating model parameters that maximizes the likelihood of obtaining the observed data. So I'm going to debunk a popular myth about maximum likelihood estimations. Contrary to popular belief, the beta parameter of this method is not the most probable value of that beta. The most probable value of beta is beta itself, but we'll delve more into this when we explore Bayesian interpretations. Old Bayesian versus frequentist arguments gets in here. But the maximum likelihood estimator's beta is simply the value of beta that makes drawing the sample actually obtained the most probable. That's why it's important to understand the asymptotic variance of maximum likelihood estimators, which is related to its efficiency as the sample size grows, which is what we were just talking about in the previous one. So an interesting feature of maximum likelihood estimators is their invariance property. Essentially, if you apply a nonlinear function to the parameter you're estimating, the maximum likelihood estimator of this transformed parameter is simply the same transformation applied to the estimator of the original parameter. That's really, really cool. So selecting likelihood estimation techniques necessitates choosing a specific distribution for the error term. In context of regression, the normal distribution is typically chosen, often justified by the central limit theorem, which we were just discussing when we were talking about the asymptotic properties. So what we're getting here is the central limit theorem states that the sum of a larger number of shocks can be considered to be approximately normally distributed. This choice is also influenced by the relative ease of working with the normal distribution, something we'll elaborate on in episodes. One more important note, while maximum likelihood estimation is an invaluable tool in an applied econometrician's arsenal, its focus is usually on the distribution of the dependent variable rather than on the error term. The transition from error density to dependent variable density involves a change of value or change of variable theorem, which we will discuss in future videos. Possibly. I'm not sure. You should probably look it up somewhere else. They'll probably have a better idea on it than I do. But anyway, when we're talking about Monte Carlo studies, what is this? This is a simulation-based method used to understand the properties of statistical procedures, especially when theoretical analysis becomes challenging. It allows us to simulate the behavior of an estimator under different conditions, giving us insights about its performance and stuff like that. It's a really cool idea. You like have a random number generator and it just goes through like 1,000 steps up to like 10,000, some of the bigger Monte Carlo studies. And a lot of econometricians, especially not applied econometricians, just pure econometricians, they'll use this to test data. So they'll know what the data generating process is, and they'll use an estimator to figure out which one of the estimators is best. And since we know the distribution of all of the things that are happening, we'll know which one gets closer to the real mean. This is important for studying things like reverse causality and stuff like that, because if we know what's going on and we're doing this like panel data test of whether we should use a structural equation model or whether we should use GMM, etc., all of these things, general method of moments, what we can do is do these Monte Carlo studies. We have the simulation. We know what the actual properties of those statistical procedures are, and then we can use that to analyze which one of these estimators or these techniques is best for that. So, and you can see here, this is the maximum likelihood estimation. This is what it looks like. And again, it's not about that beta. It's about the probability of getting to that beta. So, and there you have it. This is a whirlwind tour of chapters 1 and 2. It's going to get better, I promise. This is kind of something new that I'm going to be trying to jump into. And so we're just setting foot on this path, and the journey ahead promises to be full of intellectual excitement. So make sure to follow along as we delve into chapter 3, the simple regression model or classical linear regression, in our next video. Until then, this is the Economancer, weaving economics, theory, and practice together.